In the last section, we were discussing the electro-optic properties of KDP crystal. We found that the longitudinal configuration, transverse configuration, and the half voltage corresponding to those configurations, and it was drastically less as compared to the anisotropic isotropic material like gallium arsenide. It was of the order of 300 volt, whereas earlier it was about of the order of kilovolt, 18 to 9 kilovolt. And now there is one very important electro-optic crystal, lithium niobate. We will discuss the electro-optic properties of that, and we will see that the half voltage will be drastically down to some tens of volt in certain configurations, and this crystal is very useful from the point of view. It has other properties like piezoelectric properties. So, those are the things that we will be discussing in this section. So, these are the topics, that is electro-optics of lithium niobate in terms of electro-optic tensor, principal refractive indices under the application of external electric field, then the Z cut configuration, that is when the optic axis is along the z axis. In that configuration, the retardation and phase modulation, that we will see that in the longitudinal configuration we will see that no amplitude modulation is possible. Then we will look at x and y cut configuration, where the amplitude modulation is possible and very effectively possible, and then we will look at the half voltage, the phase modulation properties. So, let us refer to this table which I have shown you earlier. So, now we are here because we have discussed this KDP electro-optic properties of this KDP gallium arsenide, and now this lithium niobate, whose ordinary refractive index is 2.297, 2.208 is the extraordinary refractive index, and this is at the helium neon wavelength, that is around 0.633. These are the electro-optic coefficients. One can see that this R33 and particularly R51, they are very high in this number. As a result, we will see the effect is very strong in this case. Lithium tantalate also, they are under the same group and almost similar properties. So, both of these two crystals have made this electro-optic materials very rich in terms of these electro-optic properties. So, lithium niobate, 3 in 1, there are 3 very important electro-optic properties. I was talking about that. This is a combination of electro-optic, piezoelectric and optical properties. So, in one platform with one crystal, actually one can make use of this combination of these 3 properties. Naturally, it is a naturally negative uniaxial crystal, where ordinary refractive index is more than extraordinary refractive index. You may like to refer to this table. Ordinary value is more than the extraordinary value. So, it is a negative crystal, and this crystal is transparent over this region, that is starting from 0.35 visible range to within this 0.5. So, this is over this region, it is transparent, and it is a strong electro-optic effect, which is many times more that is shown by KDP or ADP. Okay. So, now this natural uniaxial crystal lithium niobate, which is very widely used as a consequence of the fact that these properties are very strong and very useful, used modulator class. There are non-zero element electro-optic coefficients, which are this R51 equal to R42. These are actually they are obtained from the symmetry of the crystal, and then values were experimentally determined. R13 is equal to R23 and R33. So, these are the non-zero elements of, but not all of them will be useful depending on the orientation of the electric field with respect to the crystal axis. So, this is the electro-optic tensor for this lithium niobate crystal, and should once again mention that this is very strongly piezoelectric. Electro-optic coefficients, I have already provided this in the table, that R33 is around 30, 8.6, 28, 3.4. So, these are many times more than the ones which we have discussed in the earlier cases like ADP, KDP. So, this values are really useful for bringing down, lowering down the hub voltage and switching of the modulator. Okay, so, let us recall that the index ellipsoid under the electric field. So, you have these changes in the impermeability, here also these changes in the impermeability, these are with the square terms and these are with the cross terms. So, I have considered all the 6 terms. Now, we will see depending on the applied voltage how this electro-optic, how this impermeability change, they are coming into the equation, which of the elements are coming into the equation. If I look at this equation, then you have considering all the 3 fields E x, E y and E z, they are acting in mutually perpendicular direction. Then these are the left hand side, which is actually a contracted notation of 3 by 3 matrix. So, this corresponds to this. So, E x, E y and E z will be multiplied to get this delta of 1 by n square 1, 2, 3 and so on. Okay. So, now let us consider a very useful and very practical case. Consider that electric field is along the z axis, that is along the crystalline axis. In that case, and also consider that light could be polarized along any direction x, y or z. The polarization of the light is but the field is now fixed, that is electric field is applied along the z axis. So, it has only E z component of the electric field. Therefore, this E z component of the electric field will make the optical property will come later. First, this electric field will excite the crystal in order to get the changes in the impermeability. So, you can see from here, if I multiply with E z, only these 3 components will be coming into the picture and that will be attached to this. So, these 3 components, because E z put all together. So, they will be added only to the first 3 elements. You can see these correspond to the first 3 elements 1, 2, 3 of this line, and the rest, that is 4, 5 and 6, they are 0. So, as a result of that, you get delta n 1, delta n 2, delta 3, sorry, delta 1 by n square, delta of impermeability 1, impermeability 2 and 3, they will have finite values corresponding to this R 1 3, 1 3 and 3 3, that is what is exactly here. So, these are the changes, and this is very interesting to note that this only changes the length of the semi major axis of the ellipsoid. So, this is under the principal axis system, that is, if I consider these changes, then this will be added to the 1 by n x square plus this 1 by n y square plus this 1 by n z square plus this. These are the things which will be added to make the new index ellipsoid, and that will represent that the length of the major axis. So, we can write in this form, but this step should come later. Let me see the first, let us explain this one, that you have the index ellipsoid originally, which was because it was naturally uniaxial. So, you have only this n z different, but n x and n y they were equal. Now, after you have applied the electric field along the z direction E z, so it is going to affect all the n x, n y and n z, but it still remains a uniaxial, and the ellipsoid does not undergo any rotation, only its size changes in terms of the new refractive indices n x prime, n x dash, n y dash, which is again not equal to n z dot. You may like to go back and see the changes. You see, this is the change with n x, this is the change with n y, but this is the change with n z. So, these two are again same. So, it maintains the original anisotropy, but the values of from the point of view of the directionality, but the values of these refractive indices in the new principal axis system changes. So, and the changes are you can represent in this way. N x dash has now become this, because this will be with the x square term, this will be with the y square term, and this is going to be attached with the z square term. So, this gives you that this is your new refractive index seen by the wave which has a polarization along new x prime direction, and this is along the new y prime direction. So, and this is along the z dash direction. So, these are the new refractive indices, which you can see that these two are again the same, they have incremented by the same amount, and this is different. So, it again remains uniaxial. So, this is a case which is very interesting, that the ellipsoid does not undergo any rotation, but its size increases, overall size increases. That means, all n x, n y and n z they increase. So, in absence of the applied field, this was the ellipsoid, and in presence of the applied field, this is the new ellipsoid, and from here only we could actually get back this numbers, this expressions for the new principal refractive indices. And okay, so now having known this fact that it only undergoes a size, that is change in the refractive indices corresponding to all the n x, n y and z to n x dash, n y dash and n z z's, to make it again uniaxial. So, there is no cross term in the ellipsoid equation, that means it does not undergo any rotation, but only the length of the axis of the ellipsoid change. So, this fact we will see that when you implement this in the case of longitudinal configuration, it is not useful to make it an amplitude modulator, because when I allow the light to travel across the crystal along the z direction, then it will see refractive indices, it will have polarizations along x and y, but in both x and y there is no rotation. So, the old axis and the new axis they remain the same, but only the values changes. So, there is a modulation of this, but these modulations are identical. So, this will not create any delay between the x and y polarized light, or x dash and y dash polarized light, which are the same. So, they will be, there is no delay between them, there is no retardation between them. As a result, any amplitude modulation is not possible. So, that is very interesting, we will see that. So, let us consider that longitudinal configuration, which is the z cut configuration, light beam is now propagating along the z axis. First, let us see that phase modulation, then we will in the process we will see that amplitude modulation is not possible. Now, that this is the configuration where you have this applied voltage, which is along the length of the crystal, the voltage applied voltage is V, length is L. So, V by L will be the externally applied electric field E z, and your input polarization, it could be along x or it could be along y, any of these, or it could be halfway through also, because in that case both this unpolarized light can also undergo the change in the phase, because both the x and y polarized light or the one which is midway through x and y polarized light, they will undergo the same amount of phase change, because they are undergoing the same amount of refractive index changes because of the external field. So, input light is x or y polarized or at 45 degree or any polarization, that polarization will give you a phase modulated light, we will see that. So, look at this once again, that this is your 1 upon n x dash square, which is equal to this, and similarly this is 1 upon n y dash square, 1 upon z dash square, and so on. So, now light is propagating along z direction, will experience, there is a mistake, will experience the same phase change regardless of its polarization states. Therefore, and unpolarized light can be modulated with such a device. Let us see that. So, now light, first consider that light is polarized in the xy plane, and with, because this is the case which will clear the understanding about if the light is polarized along x or y polarized light. So, considering that it is a polarization which is midway between x and y polarizations, that is at 45 degree with y direction. In that case, this is independent of this direction of polarization, this value n x dash and n y dash, because this is whatever might be the direction, the component in the x direction will see this refractive index. Mind that this x dash and x, they are same. Let us x dash, and you see there is no rotation. So, the direction of the ellipsoid axis, they remain the same. So, x dash and x, that is y dash and y, z dash and z, all of them they are same. So, therefore, this, if I use this notation x dash just to represent that this is the refractive index after the electric under the influence of the electric field, and this is the electric refractive index under the influence of this electric field for the y direction. So, these are actually x and y directions. So, in these two directions, the increment, the change in the refractive index is by the same amount, Therefore, whatever might be the polarization, the refractive index change is the same. In the x y plane, whatever might be the polarization, the refractive index seen by that polarization is the same, irrespective of its angle with x or y. So, then the voltage driven birefringence in that case will be equal to 0, because both of the polarizations are seeing the same change in the refractive index, and therefore, the same change in the phase. So, the phase difference is equal to 0. Therefore, no retardation between E x and E y component, or E x dash or y E y dash component we can say, because x and y are the same as x dash and y dash. Therefore, independent of the angle of the input polarization, both the components will see the same refractive index, voltage dependent refractive index, and therefore, there is no birefringence. As a consequence, there is no amplitude modulation, because if there is no delay, if there is no retardation, we cannot implement that amplitude modulation. So, this is very interesting property for a Z-cast lithium niobate crystal, which is a property because of its the nature of the electro-optic tensor. In the longitudinal configuration, however, the voltage driven phase change, because this part, this is there. So, any polarization the light is launched, that will undergo a phase change. This is the phase change which will be just because of the voltage, and then for that half voltage. So, that is the case of phase modulation, half voltage is equal to this, and if you put the typical numbers for this, that those are the numbers which we have used earlier, then V pi will be equal to 5.5 kilovolt, which is large, fairly large, of the order of kilovolt. But since there is no retardation between any two orthogonal polarized waves, therefore, there is no amplitude. That is the most important outcome, that it cannot be used as an amplitude modulator, but it can be used as a phase modulator. But in that case, you have the freedom that it does not require any polarization. Any polarization across x and y, wherever is the polarization angle with x or y, it will undergo the same phase modulation when the external field is applied. So, the light polarized in the x y plane with 45 degree with under this condition, this is the change we have seen. Then the voltage driven phase change z for the z propagating light will see this. So, that is the phase modulation. So, with the voltage V, the phase will be modulated. So, delta phi is the same for x y or x y polarized light. This repeatedly I tried to mention that independent of the angle of polarization in the x y plane, any light will undergo the same phase modulation because of the applied voltage. Now, we will see the transverse configuration. A beam is now propagating along x axis or y axis, and we will see that this time the amplitude modulation is possible. Input polarization will be at 45 degree. The condition is the same because you are applying the electric field along the z direction. Look at the orientation. Now, I am applying the electric field along the z direction, but the light is now propagating along y axis, or it could be as well along x axis. So, we considered this situation because x and y they can be spatially inverted. So, input polarization is 45 degree with x axis, output polarization this will be at crossed position with the input, and there is a compensator. We have learnt very well why we need a compensator, because you have to push the operating point at 50% transmission. It could be as well done by applying an additional bias voltage, but this is more preferred, this we have seen earlier. So, now considering this, once again you have this these are the refractive indices seen by x polarized light and z polarized light. You can see that now these two are different values because of 1 3 and 3 3. As a result, and also the base refractive indices, the the refractive indices in absence of the natural refractive indices along this x and y are OE and NO and NE. So, that is also creating a difference. This is the natural birefringence and this is the induced birefringence because of the external electric field. So, retardation at a distance y. So, the light has travelled through a distance of y, So, over this distance, now it has accumulated phase which will result in this retardation, that is delta phi, which will be equal to this into this, very straightforward from here. This is the induced retardation and this is the intrinsic retardation because of the natural values of the refractive indices along the y, x and z direction. So, this part requires some has to be compensated for changing the operating point, shifting the operating point for linear operation, whereas this part is the voltage induced birefringent. So, the phase shift over a length L, this in absence of any field, which has to be compensated by optical bias, the thing that we have already discussed in the case of KDP crystal. You may have to use a compensator, Wavinette-Solel compensator, to operate at the modulator at the linear region. Okay. So, now this induced phase shift in this case is this, because if we assume that we have already compensated this part of the phase and we have shifted the operating point to work at this region, then you have induced phase shift is this, which will correspond to a phase shift of pi, and you will get a half voltage, that is the voltage required to switch the modulator from 0 to 1 state, which we have discussed. That depends on the width and length ratio as well here in this case, and these values are very high, R33 and R13. We have shown you in the first occasion that these values are of the order of 30 and so. So, this the effect is very strong because of the strong coefficients. So, geometrical parameters, typical practical numbers which are used for the practical modulators, the d equal to 0.25 millimeter, L equal to 9.5 millimeter. In that case, you get this lambda equal to this, and your this value. So, if you plug in the values of R33 and R13, D and L. So, putting all these things, you can see by if I use this equation, you get a half voltage of the order of 64 volt, which is drastically, one can see that the half voltage is remarkably less than that of for KDP or ADP. It is a great big achievement that under this configuration, under this orientation of the crystal with respect to the electric field with all these parameters, you can bring down the switching voltage to from kilovolts, from tens of kilovolts to only tens of volts of the order of 10 to the power of 3 down. Now, phase modulation with this transverse orientation. So, it is again the same configuration, light is propagating along y. Now, instead of the input polarization being, that is the principle we have been repeatedly saying that for phase modulation you have to place it along only one of the axis x or z, but if it is amplitude modulation you have to place it halfway through. So, that you can excite both of them, but in this case we will excite only one polarization, and the beam which will be available here will undergo phase modulation, just because there will be a change in the refractive index which is voltage induced. So, this is the configuration. You have this will only modulate N z if you have z polarized light and propagating along the y direction. This is the refractive index. Then the phase emerging beam will be phi equal to this much. So, this is the intrinsic phase because of the propagation over this length L, but this is the phase which is the accumulated phase because of the external electric field E z applied across the crystal, and this is going to change the refractive index. So, the modulation will come from here, this will remain the same. So, this hub voltage in this case, if you plug in the numbers, because you have only R 33 and there is nothing to be subtracted from here. So, this value is more, and V pi by d we can write in this equation. So, V pi comes down to this value, this expression, and if I use the earlier numbers for this case, these numbers, then you can show that your hub voltage required is even less, that is V pi is about 48 volt, which is very useful and to utilize this as a modulator for phase modulation of this. So, in this case we have seen that the amplitude modulation, for amplitude modulation you can see that the hub voltage is 64, but for the case of phase modulation it is even less of the order by some amount, that is about approximately 48 voltage, which is. So, this electro-optic system we will see in the next section, that how these various crystals can be utilized for the properties for the modulation purposes and designing devices and modulators, and that will be very useful. Many of the things are commercially available and the research is still going on. So, thank you very much.